Okay, I think we will go ahead and get started. Good afternoon, everyone, and welcome to our new series for the AI Experts Network, the AI Innovation Lab series. As you can see, I'm not Timothy. I'm covering for Timothy today. We hope that you have been enjoying our new series and this time to collaborate and make a difference together. We will only be having 3 more sessions in the AI Innovation Lab series in 2023. If you are interested in leading a lab session or are interested in hearing from someone or have a specific topic in mind, please reach out to me or Timothy with that topic. Thank you for transitioning with us from the Xavier Health. At the Active Reps Healthcare Collaborative, we are continuing to host the AI community that has been growing and thriving since 2017. Not only do we have this AI expert network that has been specifically designed for you so that you can talk shop right away without having to stop and go over the basics, but we also have our AI Summit. We will be returning to Cincinnati this year, so please save the date in your calendars for the AI Summit, which will be held November 14th through the 16th. Registration will be open soon, and we hope that all of you will join us for this summit. Many of you are familiar with the Active Reps Healthcare Products Collaborative mission, which sounds like the mission you were familiar with at Xavier Health. Not only are we continuing that mission, we are also continuing the AI Expert Network mission that was started there to establish a collaborative forum of AI experts across academia, government, and industry in accelerating the development of AI solutions for the benefit of global healthcare community. Now more than ever, this mission is critical. These lab sessions focus on being a community where we can have discussion, the free flowing of ideas, and a place where like-minded people, especially in AI, can have discussions. Akhilesh, I'm going to turn it over to you to introduce our speaker.
Excellent. Thank you very much. So for today's speakers, we have Lane giving us the talk. And Lane Despero is an engineer, you're an entrepreneur and innovator in the field of industrial automation and diabetes technology. Lane started his career in the late 80s working on safety critical automation systems for chemical plants, oil refineries, mines, pulp mills, and power plants all over the world. In 2009, nearly after 2 decades at Honeywell and General Electric, his son was diagnosed with type 1 diabetes. And that's when Lane soon found himself at Medtronic Diabetes, leading the engineering team responsible for the next step towards the artificial pancreas automated insulin delivery devices. In 2014, he co-founded the Bigfoot Biomedical, and as Bigfoot's chief engineer, he developed safe and effective scalable systems to reduce the burden of insulin requiring diabetes. In 2020, Lane, you founded the Nudge BG, an engineering consulting services and algorithm development company focused on modeling, simulation, and control of physiological systems. So Lane, with that, I'll probably pass it over to you to get started. The floor is yours.
Excellent, thank you. Can everybody see me and hear me okay?
Yes, we can.
Okay, cool. So the title of my talk is deliberately intended to be a bit provocative today. Algorithms, the apex predators of the software that is eating the world. Over a decade ago, Marc Andreessen had a very provocative idea that software is eating the world. I think, having been involved in automation my entire career, that this blog post is actually more accurate, that it's automation powered by algorithms that in fact is how software has been eating the world. That automation, some or all aspects of billions of sense decide act feedback control loops, from car cruise controllers to home thermostats to aircraft autopilots to chemical plant control systems. That's what has in fact been making the biggest difference. So from this, I posit that algorithms are the apex predators of the software that's eating the world. And what are some of the implications of this? I'll be focusing on automation algorithms and not AI/ML in particular for 2 reasons. The first is I'm not an expert in AI/ML by any stretch of the imaginations. And 2, these algorithms for automation have been around for a really long time, all the way back to things like the flywheel governor of James Watt's steam engine, or the automation of this poor man who's sitting on a one-legged stool to monitor the temperature at an explosive plant. You can imagine that was a great day when his job got automated. So I was taught in grad school 3 decades ago that the purpose of automation is to safely transfer variability from a place where it hurts to a place where it doesn't hurt as much in order to make a human's job easier. So if you consider something like a car's cruise controller, it's transferring variation in speed to variation in fuel consumption. So whether we're going up or down a hill or have a headwind in or tailwind, we just want to drive 65. We don't care if we're using a little more or less gas to do so, but we just don't have to do as much work. That's really the promise of automation, and you can see how it's been applied in all these other domains. Okay, so cyber physical systems. So this is a cyclohexanone plant that blew up in 1974, killing 20 people. A key learning from this accident is that they kept too much inventory on site. There was too much stuff around when the explosion happened, which is why it burned for 10 days. And there was an important set of lessons that the chemical industry took from this tragic incident. One of them was that which you do not have does not explode. So keep that in mind. I'm going to bring that up later. So in the 70s, these plants were largely under either manual or primitive electromechanical control. And nowadays, they're all controlled by computers, often from off-site control rooms located a kilometer away, sort of outside of the nominal blast radius, which has some implications in human factors that I'm going to talk about in a minute. This petrochemical plant control is an example of a cyber physical system. The cyber interacts with the physical. The physical involves potentially large and dangerous amounts of energy being exchanged. So software is no longer harmless mental abstraction like a video game. These software algorithms are controlling large amounts of energy, potential and kinetic energy of aircraft in flight or automobiles, thermal energy of homes and power plants with HVAC and thermostats, chemical energy of petrochemical plants, electromagnetic energy of power plants, nuclear energy of nuclear power control. So this is something that we just really need to be mindful of, that when you're using software to control cyber physical systems, the stakes are pretty high. So this is my first cyber physical system. It was the automation of a pump cable test lab while I was still in undergrad, a very long time ago. So here you can see the cutting edge printer and data acquisition and compute platform that I built in 1988. I think it was Turbo Pascal and IBM PCAT, but this homegrown SCADA system used PID feedback control algorithms to control the pressure and temperature in the vessels that you can see behind the wall there, simulating downhole conditions in an oil well. And today, something like a $5 Raspberry Pi is 100 times more powerful. We've come a long way. After grad school, this is the chemical facility that I went to work for, Nova Chemicals in Joffre, Alberta, Canada. And it's got a pretty big site. There's 3 ethylene plants, 2 polyethylene plants, linear alpha olefins plant, hydrogen off gas plant, power cogen facility. It's one of the largest facilities of its type in the world. It's big. How big? About 6 billion pounds of ethylene per year. Managed by something like 5,000 control loops, all supervised by about 15 control room operators. So you think about the scope of responsibility, how much chemical is being produced in this one facility, all being supervised by about 15 operators. So it's emblematic of the degree to which these apex predators can have a very positive impact on people's lives. They're not in that dangerous blast zone, or not as many of them anymore. So this plant is a good example of a continuous process industry facility. And it was a fantastic place for me to learn about automation. So during my time at Nova, one of the big projects they worked on was the modernization of the control system at one of the ethylene plants. So going from the thing on the left to the thing on the right. But I got involved in all aspects of the automation stack, from low-level PID control, model predictive control, real-time optimization, all the way up into advanced planning and scheduling. So this concept, by the way, is called hierarchical feedback control, and I'm going to touch on that in a few minutes. From Nova, I was recruited to work at Honeywell and later General Electric. Honeywell is the world's largest provider of industrial control systems. I spent 15 years implementing and remotely monitoring automation all over the world, from the oil sands of Alberta to the savannas of South Africa, to the jungles of Brazil, to South Korea, and the largest single site oil refinery in the world, to the front end of the US nuclear supply chain, where all the yellow cake comes to get processed into uranium hexafluoride. Thousands of feet underground in mines. Maybe 100 control rooms. I've lost count of how many control rooms I've been in. And honestly, I just can't imagine a better career. I was very lucky to have been exposed to so many cultures and to interesting processes that we take for granted in our world. Where the gasoline comes from, or why our temperature is a nice 73 degrees in our house. I got to see what's going underneath, how algorithms are really powering the cyber physical system world. These are some of the cyber physical system algorithm projects that I worked on for the first 2 decades of my career. And I just want to note, I'm not going to go into any detail on these, but all of these are industrial projects at commercial scale. These aren't academic research papers, toy solutions to toy problems. This is how did we apply algorithms at scale to solve real world problems and create value. All right, so talked a little bit about cyber physical systems. Now I'm going to talk about the data, which is the underpinning of how we build algorithms and what some of the challenges and opportunities are there. So when I was doing consulting engineering, implementing control at these very large facilities all over the world at Honeywell, a big part of the job of implementing automation is identifying models of the plant. And to identify models of the plant, you should hopefully be looking at data from the plant and maybe even doing some experiments. And what we found is that the other engineers that I was working with didn't really have sufficient background to do this effectively. And so I was chartered to develop a course to help fellow engineers to go through this process of making sure you're doing a well-designed experiment to yield good experiments. The good experiments yield good data that yield good predictive models that can be implemented in model predictive controllers that can then drive value. So this course was, or this course was later turned into a grad school course and taught in university. But this sort of highlights some of the many pitfalls to turning data into action, and let's review a few of these. So first of all, it's difficult, time-consuming, expensive, and sometimes even unethical to perform experiments to get good data. The data generated by these experiments, once you've done them, is often messy, hard to replicate, has many other problems. And unfortunately, all of this propagates downstream to poor models and poor outcomes. So I love the aphorism, the biggest mistakes are made on the first day of the project. That's when you have the biggest leverage, is to do good experimental design. So this is exactly the case here. Poorly designed experiments, or worse, just using data that's laying around, will usually yield poor quality data. It all goes downhill from here, garbage in, garbage out. Quick little segue, and this is something that was posted a couple days ago. Garbage in and garbage out is still a problem with AI ML algorithms, as noted by Cory Doctorow in these posts here. When it comes to AI that's used for decision support, that is when an algorithm tells humans what to do and they do it, then you get something worse than garbage in, garbage out. You get garbage in, garbage out, garbage back in again. That's when the AI spits out something wrong and then asks an AI, then another AI sucks up that wrong conclusion and uses it to generate more conclusions. So lots of good examples in that post there. Okay, back to the regularly scheduled program here. Problems with data and experiments. Here's a specific challenge. Experiments designed to yield maximum information content are often unsafe because you're pushing the boundaries, or should be, while safe operation of a feedback control algorithm often provides low information content. You don't learn very much from a thermostat that's maintaining the temperature at 73 degrees. So the objectives are diametrically opposed. This is why one should be really careful when offered closed loop data from which to build models and algorithms. So stated simply, you learn more by poking a lion than by watching one in a zoo, but poking is pretty dangerous. Okay, so once you've got data, there's many statistical perils with building algorithms. I should, full disclosure, I am the academic great-grandson of Dr. George Box of All Models Are Wrong, Some Are Useful fame. So I come from a very strong bias of rigorous statistics and simplicity. George Box literally wrote the book on time series analysis, forecasting, and control. So I do come in with this strong belief that we need to really understand and apply solid statistics. And from that, I would hope that it's clear that complexity is not necessarily better, that complex models do not automatically confer goodness. In fact, in this awesome paper, I tell everybody about this paper, the circumstances in which models, simple models outperform more complex models are made very clear. The paper also highlights a really important distinction between the predictive capacity of a model and the explanatory capacity of a model. So just because one is good at explaining doesn't mean it's good at predicting. So I think this really highlights the importance of understanding an algorithm's context of use. What are you going to use this algorithm for? Is it for prediction or for explanation? Or in the case of something like feedback control, are you using that algorithm for set point tracking of a set point that's moving around, or are you using it for disturbance rejection? And it's important to have a deep understanding of the problems that the algorithm is trying to solve. Otherwise, you're not going to get the outcomes you're after. So this is all to say the blind application of the latest methods to blobs of data that might just happen to be laying around may not yield good outcomes. Again, the importance of understanding the statistical properties and the potential presence of closed loop and doing well-designed experiments, all of these are going to set you up for success. So before embracing the latest algorithms, I think it's really worth examining if simple algorithms can do the job. I've been a fan of Dr. Eamon Keogh for 2 decades. He's at UC Riverside. We both strongly value simplicity. He recently published some, I think, profound insights on data and benchmarks used in anomaly detection, which is one of the key time series use cases of how do we detect an arrhythmia, or how do we detect whether a transformer is failing? So he provides some, I think, really compelling examples of one-line algorithms which do as well or better than contemporary methods, which are, of course, these one-liners are transparent. You can see exactly what they're doing. Okay, so human factors. By the way, we should have lots of time for questions and comments. Human factors. So we build and deploy these automation algorithms to help humans transfer and manage variation in their environment. And feedback works this way. We sense something with a sensor. We decide what to do with a control algorithm. And we perform an action with an actuator or final control element, which affects the thing being controlled. So sense, decide, act, closing loop, feedback control. What is often missed is that each of these tasks, sensing, deciding, and acting, can be performed by a human or a computer, or a combination thereof. So that sets up these levels of automation ranging from full human control to full automation. And where we tend to get in trouble is in the middle period, the middle where some parts are automated and some parts aren't. In addition, many miss the fact that new tasks are in fact added with automation. So we think about automation as a panacea and, oh, look, life will be great if we just automate everything. Well, the human gets some new tasks, and some of these tasks are quite difficult. Supervising the automation, troubleshooting the automation when it has a problem, because now there's all these parts of the system that weren't there before in the manual case. Performing maintenance on the automation. Those are complexly cognitive tasks. Automation shifts the user from being in the loop to being on the loop, or even worse, being out of the loop. There's some huge challenges with reinserting yourself into a loop if you've lost situational awareness. So in the late 80s, a series of major incidents, petrochemical plants blowing up, led to the realization that human factors was a major cause of accidents. Something like 40% of the $16 billion a year in losses were found to be caused by humans and automation not getting along. So the oil companies did a very unusual thing, and they said, we're going to compete on everything else, but we're not going to compete on safety, because when a refinery blows up, general public doesn't care whose refinery blows up, everybody gets a bad name. So let's pool our resources. Let's form this abnormal situation management consortium and pool our learnings and channel them into a single technology provider industrial anchor, Honeywell. So I happen to be working for Honeywell, and this ASM consortium still exists today. And I was privileged to be a part of this consortium for about 15 years, understanding how do we take lessons. And by the way, part of the reason that Honeywell was the anchor for this was Honeywell had experience in other domains. So Honeywell does avionics, Honeywell does HVAC control. And what they were able to do is take some of the learnings that had already been gathered and applied in these other domains and say, well, let's just apply them to industrial process control. So there's this joke that the plant of the future will be so automated that it will have one human and one dog. The human's job is to feed the dog, and the dog's job is to keep the human from touching anything. So unfortunately, dogs won't be controlling chemical plants or driving cars or flying airplanes anytime soon. Humans will still be interacting with automation to control these safety critical cyber physical systems for the conceivable future. We still need humans. Therefore, there's much we can and should learn from these other domains that may seem disparate, but I think we'll find there's the same human sitting in that cockpit or that control room with the same biases and capabilities and objectives and tasks. So, for example, properly allocating tasks is critically important when considering automation. The human has information about the past, the present, the future, which is unavailable to the computer. The human's got 5 senses. The human can deal with the novel, whereas most computers can't. And on the flip side, computers never get bored. They will keep doing the same thing forever until you tell them to stop. So there's some tremendous opportunities for task allocation where we give the human things to recognize. So the blinking the recognition prime decision making, and we give the computer the thinking tasks, the rote tasks. So systems with these particular characteristics, so if you don't design your automation algorithms properly and don't do an effective job with human factors, you're going to create some new problems for the human partners and new forms of system failure. So the human and the automation must have knowledge of each other's intent. And we should be designing these systems that we are creating alignment of these intents rather than divergence of these intents as time goes on. When humans are removed from the loop, so when they go from being in the loop to on the loop, or worse, out of the loop, bad things can happen. Obviously, they become de-skilled. They can lose their familiarity with the stick of an airplane. You know, they can forget how to fly. They can become complacent or even addicted to automation, where they get to the point where they're afraid to turn it off and take control. I've seen this happen before, where the operator should have intervened, but they didn't because they didn't know what would happen if they turned the automation off. So this results in getting off of what's called the trust calibration curve, where they may over or under trust the automation. So you don't have appropriate trust of automation. And worst of all, during critical situations, they can get distracted or overwhelmed or otherwise unable to reinsert themselves into the loop and make the necessary control or maintenance actions to save the day. So you've got this huge challenge of the computer forgets how to do something, you know, gets into a regime where they don't know how to deal with it. They hand it back to the human at the worst possible time. The human has to reinsert themselves into the loop. Lots of challenges there. So in cockpits and oil refineries and other cyber physical systems, the users, these pilots and operators, often find themselves confused by what the automation algorithms are doing. And what I find amazing is across industries, they ask the same questions, often at the worst possible time. Such as when the automation is given up and handed control back to the user. I don't know how to fly this plane anymore, you take it. All of those issues can be addressed by proper design. One facility that I worked with went to great lengths to develop this fancy algorithm, multivariable state estimation using principal component analyses, taking this multi-dimensional set of data that was flowing in and summarizing it into its principal components. And they came up with this radar plot for the operator. And during a abnormal operation, it would go from good to bad. And the operators called it the sphincter plot because it really provided no directly actionable information, only an indication that something bad was happening, you better buckle up. And as the operator said, this thing blows a lot of smoke, but it doesn't show the source of the draft. So this is an example of potentially a good algorithm with poor human factors and transparency leading to not achieving its outcome. Okay, so over the next few minutes, I'm going to share some specific methods, tools, and practices from automation algorithms in cyber-physical systems. So first of all, chemical engineers like me have been dealing with pretty large volumes of mostly time series data for a very long time. A typical refinery might be generating, I don't know, 100,000 sensor values a second. A gas turbine combined cycle power plant is generating 1,000 samples at 60 hertz, so 3,600 samples a second. There's a lot of data flowing through these systems, and we've made a career of turning this data into a variety of data products. So some of them might be low-level feedback control algorithms, some of them might be higher-level real-time planning and scheduling, some of it might be operator decision support systems. So I just want to point out, and I've seen this throughout my career, that there can be a wide and deep body of knowledge in one domain that people just don't even know is there. And, as an example, if we think about something like the Z-transform is an electrical engineering concept. If you go into the econometrics literature, they call it the backward shift operator. If you go into chemical engineering, they got a different name for it. The point is, it's the same thing. And when you know that, you can go tap into these other domains. So for instance, one of the first algorithms I worked on was surge detection in a very large gas compressor. And the tool I used was SAS Econometrics Toolbox. This was 35 years ago. Okay, so there's a narrow but deep pool of automation factors research that's been amassed across other domains. So I'm being careful to specify that I'm talking about automation human factors, not general human factors. And I've posted here a summary of this as feedback to an upcoming FDA physiologic closed-loop control guidance document. So you can go read the guidance document, you can go read my comments, annotated bibliography if you're interested. So there's a ton of information out there on how do you successfully put design around algorithms to make them usable by the humans who are the partners in the cyber-physical system. Another example, so in other industries such as automotive and aviation, where the commercial reach exceeded the technical grasp, in other words, engineers were being asked to do things which were impossible with the tools at hand, the engineers had no choice but to develop new methods to characterize these complexly interactive systems. This is an outstanding paper from some of the folks at Toyota. This has been a hack of mine for the past, I don't know, 30 years, is go look in other industries who might be decades ahead and just steal from them. Just apply their methods. What do they call it? Proudly found elsewhere versus not invented here. Here's an amazing woman, Dr. Nancy Levison, who's been studying cyber physical systems for decades. She's got a new book coming out. This is one of her older books, outstanding. You can download it online for free. But I think she makes some very provocative and important points about these cyber physical systems and the role of the human, and what does safety mean? What does failure mean? How do we protect against them? And some of her methods are extremely powerful and now starting to be deployed very widely across multiple domains, things like STPA, if you've ever heard of STPA. So been a big fan of Nancy for a couple decades now. I do want to touch on the topic of complexity for just a moment. So for a variety of good and bad reasons, we're now dealing with complexity on a scale that we've never seen before. So what happens when you start to interoperate systems that were never designed to be interoperated? What happens if you are dealing with software and algorithms that are extremely complex? What if you're tackling problems that have been intractable with the method? So I think it would be wise for us to look at how others are managing this complexity. Algorithms, as I mentioned earlier, they're the apex predators, they're very powerful, and with great power comes great responsibility. I think we need to be really careful, even with something as simple as exponential smoothing. So here's a very simple one-line algorithm. It's a snippet of some C++ from a medical device I reviewed a few years ago. And there's one line of code out of tens of thousands. Do you notice anything wrong? Well, there's a plus sign in front of the equals. One innocuous little character, one character in a massive source code. And unfortunately, the algorithm intended by the algorithm engineer doesn't have a plus sign. So you think, oh, yeah, one plus sign, big deal. Well, that plus sign has an undesirable effect on the result. It changes the intended algorithm to a different algorithm with some unintended consequences, as you can see here. It goes from being a nice smoother to going nonlinear very quickly. So this is an example of what happens if we are not careful in managing the complexity. If one plus sign can ruin your day, imagine what else can ruin your day. So I've been battling complexity my entire industrial career. Complexity is what intimidates me the most about algorithms in general and AI ML algorithms in particular. One misplaced character in a million lines of code can kill somebody, and it has, or resulted in a spacecraft accident or a loss, or a chemical plant blowing up. So if the act of writing software is the act of writing bugs, because even the best code in the world, things like the space shuttle control code, has defects in it. So the act of writing bugs is the act of writing code. So logically, the only way to avoid bugs is to not write software, which is back to the Flixborough example of keeping a large inventory as a recipe for disaster. It's the same with software. The software that you do not write does not have bugs. So this is my mantra, is keeping software as simple as possible and using well-established practices in software governance. So really applying the methods, tools, and processes from other industries who have been battling this complexity for a lot longer than we have. And these are acronyms. You can Google them, or just reach out to me if you want more details on any of these things. But I think we do have this advantage that so many industries have built these tools, and now we can sort of take the peace dividend from the investments made in those tool chains across other industries when we get into medical devices. So finally, I hope it's clear that fielding safe and effective cyber physical systems at commercial scale takes a village. It's not just about being an algorithm expert and knowing something about algorithms. You need to know about human factors, and you need to have a system engineering hat on, and you need to have design experience and domain experience. You need to know the context of use and the problem you're trying to solve. It really does take a village. Okay, so a quick case study on automated insulin delivery. 14 years ago, our family's life took a pretty sharp turn when our son was diagnosed with type 1 diabetes. Didn't know anything about diabetes, no family history. And that really set us on a different path. As an example of that, to the list of energies I shared earlier, I propose to add another. Don't have a great name for it, so I'll just call it biologic energy. Biologic energy, insulin lowers blood glucose. Glucose is a key energy source. So too little or too much insulin will kill somebody with diabetes pretty quickly. This is a picture of my wife, an RN, administering an IV to our son to mitigate the effects of insufficient insulin, something called diabetic ketoacidosis, which will kill you and will put you in hospital. So prior to the diagnosis or the discovery and isolation of insulin 100 years ago, everybody died with diabetes for lack of insulin. So it was a terminal diagnosis. So this managing of blood glucose with insulin is a pretty important concept. And now, through the careful delivery of insulin, blood glucose can be managed for people with diabetes, and they can live normal lives. That's the good news. The challenge is that doing this manually is pretty difficult. So this physiologic closed loop, again, like others I've shown, involves sensing, deciding, and acting. So for somebody without diabetes, the endocrine system does this all by itself. But for somebody with type 1 diabetes, they need to sense their blood glucose, maybe prick their finger and do a finger stick. They need to estimate their meal carbs, how many grams of carbs in that bagel, decide how much insulin to take to keep blood glucose in a safe range, given those inputs, and then perform some action to inject the insulin through a syringe or a pen. So this is a case of the human is in the loop, manually doing all of these things, manually sensing, manually deciding, manually acting. And I can say from personal experience as the father of a child with type 1 diabetes, this sense, decide, act task carries huge risk and huge burden. It never stops. You're doing this 24/7 for the rest of your shortened life. So this burden falls mostly on the person with diabetes, but also their loved ones and their healthcare professionals. So I was pretty compelled by the opportunity to automate this, having come from these other heavily automated industries. So automation of the sense, decide, act task removes the human from this tyranny of being in the loop and changes their position to being on the loop. That's good. And it frees or pardon me, I should say, it also creates these new challenges I've mentioned before, that now you have to supervise the loop. So there's a supervision task and the challenges of maintaining situational awareness, inserting yourself in the loop at the right time, troubleshooting what's going on, because now these things are complexly interacting, and performing maintenance on things you've never maintained before. And by the way, this applies not just to the low-level automated insulin delivery loop that typically happens every 5 minutes, where you've got a continuous glucose monitor sending values to an algorithm on an insulin pump that's making small changes to insulin. That's the lowest level loop. I think there's huge opportunity for these other loops in the hierarchy. So things like remote monitoring. So when your kid goes to school or is playing soccer and you're on the side of the field, or going over to grandma's house for a sleepover, remote monitoring algorithms, clinician decision support algorithms. So the physiology and behavior are changing all the time as people go through their lives, and you need to update the gains of the system. That's a really hard job, and clinicians could strongly benefit from some clinician decision support tools. Adverse event reporting, so things like the MAUDE database of the FDA, and putting that into a feedback loop. Things like the PCCP, the predetermined change control plans that we're now starting to see are an element of that. So post-market vigilance, how do we shift from focus on pre-market to taking more post-market vigilance, post-market evidence? I think that there's a huge opportunity there, even things like population health. Okay, so I think it's really important to keep in mind that the system in which these algorithms operate is complexly interactive. So just look at all the flows of data happening here. So consider blood glucose being sensed by a CGM algorithm, which has some error or drift. It's passing into a notification system algorithm, which presents an alarm to the user. These humans have varied responses to alarms. Some respond quickly, some respond slowly. These responses are often informed by the reliability or accuracy of the alarm algorithm. So if you get too many cry wolves, you're not going to be as responsive to alarms. And at the end of the day, the alarm may trigger a carb rescue or correction bolus, some intervention by the human, which may in turn have an effect on blood glucose, which may in turn affect the algorithm in its response. So you can see all these interacting paths. I hope it gives you a sense of just how difficult it can be to anticipate the risks of these component interactions during design and development of these automated insulin delivery systems. I have to admit, when I got into this 14 years ago, I thought this is such a simple problem. This is a single input, single output controller. I've been dealing with these 30 by 30 controllers at the biggest refineries in the world, and I'm still amazed by how challenging this particular seemingly simple task is. This complex interactivity, for example, has produced unanticipated and undesirable second-order effects, thanks to the law of unintended consequences, or what's known as the Cobra effect, where some of these algorithm design interventions were made with the best of intentions that had unintended consequences. So there's a couple examples from automated insulin delivery. And ultimately, these should have been anticipated and mitigated during design. And furthermore, there should be post-market feedback loops which afford rapid detection and updating when these things are discovered. So there's, back to this point about the human and the automation algorithm should be partners, and they should be aligned rather than diverging. That last example where there were constraints put on how insulin gets delivered. Well, the human quickly figured out they could cheat and tell the algorithm that they were eating more than they really were, so that they could get more insulin and get more aggressive. So that was a workaround and a cheat, which now resulted in this divergence and further challenges of modeling, because now all of the records are showing the humans eating twice as much as they really are. So on top of all of the challenges I mentioned earlier about complex interactivity, diabetes data sucks. There are 50 or so sources of variation in blood glucose for people with diabetes: stress, aerobic exercise, anaerobic exercise, hormones, medications, illness, sleep, alcohol, carbs, fat, protein, blah, blah, blah. We don't measure any of them. Or if we do, it's very difficult to measure them. And the handful that we do measure, we measure them poorly. So they're not very accurate. And they have all of these challenges that are identified here: small samples, collinear inputs. And what I would say is this is probably not specific and limited to diabetes data. I suspect many other health and medical data examples or contexts have a similar challenge when you're trying to do algorithm development. Oh, and another detail: most of this data is hidden in corporate fortresses or otherwise inaccessible for privacy or legal reasons. So even if the data is being collected, you probably can't get at it. It's hidden in Medtronic or Tandem or Insulet or Dexcom. All right, so summary, and then I hope you've thought of some questions or comments. Oops. How did that happen? So in summary, algorithms have the potential to positively impact medicine and healthcare and medical products in many different ways. So the sense, decide, act loop exists on multiple levels and can provide benefit from diagnosis up to therapy, all the way up to population health management. But I don't think we should be cavalier about how we manage these algorithms through their life cycles. They're embedded in cyber-physical systems that are interacting with the real world, managing large and potential amounts of energy, including this biologic energy. And I think we just need to be mindful of that and take lessons from these other domains. By the way, this picture here is from that same ethylene plant where I worked, where there was a innocuous software update made to one of the control stations in the control room that revealed a previously unseen bug, which immediately fail-safed every valve in the plant. So the plant was going full bore. All of a sudden, all these valves slammed shut and really bad things happened. And there's no reason to expect that this wouldn't be happening in our domain if we're not careful as well. So I just wanted to say that I am in full support of deploying algorithms to improve health outcomes. But that being said, I think there are many challenges. Fortunately, these other industries have developed a wealth of experience and a powerful set of methods, tools, and processes, which we can and should directly benefit from. So I'll end with my favorite quote from science fiction author William Gibson: "The future is already here, it just hasn't been evenly distributed yet." Thank you.
Awesome, Lane. This was really informative. And maybe we can open the floor to questions. Does anybody have any questions? Feel free to unmute yourself and ask to Lane, or you can also put it in the chat, or we can answer it through that as well. And I guess while people are thinking about questions, Lane, I do have one question actually. So this is definitely very informative, and the aspects which you told about the physiological closed loop control, the PCLC, and the FDA guidance on that. Just curious. So recently I've come across, like in the insulin pumps, use of machine learning and reinforcement learning is being investigated. Since you have a lot of experience, like, is it already out there or from an automation standpoint or not? And then also, what would be the agency's take on having machine learning in the control loop for doing a lot of that automation?
Excellent question. What I would say is that we are probably starting to see some AI ML applied, but probably in areas which are not directly part of medical devices. So those higher level loops that I showed earlier, things like customer support. Customer support is a very challenging task in an automated insulin delivery system. So when you go from being an insulin pump provider to being an AID system provider, now you have all this complexly interactive behaviors to deal with. How do you provide consistency and clarity of what might be going on when somebody phones up customer support, says, my blood glucose is 400, I don't know why, help me diagnose this. I think that there's some opportunity and some things already being done in AI ML in those domains. And we will probably over time start to see some of these algorithms used further down in things like decision support systems. So we're seeing that as well for clinician decision support. There's some examples out there. For instance, DreamMed has got a titration algorithm. I think there's a couple others. One of the challenges, though, is that you do need to fit things on a tiny little SoC, a tiny little MCU. So I think there is perhaps some limit to the compute power that is available on these body-worn devices. Did that answer your question?
Absolutely. That totally makes sense. Thank you for sharing that. I think we have another question in the chat.
Yes, I see that. So the question is, how is my son doing managing his diabetes? What BG system operations does he find most beneficial? So he's now almost 24. Or when people ask how old he is, I say he's 20 with a standard deviation of 6, because he's still maturing. But 4 years ago, he was not wearing an AID system. He was not even wearing a continuous glucose monitor. It was extremely dangerous. He was going to kill himself eventually with this. And part of the reason he wasn't wearing a CGM was you can't turn the alarms off. The alarms are driving him crazy. And so we worked with him to start wearing a CGM again. And we were able to get him access to this insulin pump here from Tandem. And it completely transformed his life. So he went from being very unsafe and hugely burdened by diabetes to being able to get on with life. And for those of you who know anything about diabetes, this thing called HbA1c is the way that you sort of quantify blood glucose levels. People without diabetes have an A1C of around 4.5, 5. Somebody who's tightly managing their diabetes has an A1C of around 7. His A1C was over 12 when we started him on this system, and within 10 weeks, it was down to the mid 7s. So it completely transformed his lived experience, as I figured it would. And this is why I'm such a proponent of the use of these algorithms, if you do it carefully. Great question. Thanks for asking.
Very cool. Lynn, I have another follow-up question on that. One of the trends, what we've been hearing recently in the medical industry is about interoperability. And just curious, we talk about the big hospital systems and interoperability between the devices, like a ventilator with a cardiac monitor, for example. But sounds like even in this case, like with insulin delivery and the continuous glucose monitor, right? These are devices manufactured usually by other companies, and this has already been proven, I guess. So just curious, does interoperability have any play in this?
Absolutely, it does. So, in fact, the two leading automated insulin delivery systems today rely on interoperability. So they don't come from a single vendor. You've got a continuous glucose monitor made by one company, an algorithm maybe licensed from another company, running on an insulin pump from another company. So this is another opportunity to leverage what's been going on in other domains like commercial aviation or automotive, where we've had this whole set of suppliers who have figured out, how do you do software-defined cars? How do you do software-defined aircraft? How do you do software-defined medical devices? That's what we're really into now. So things like standards, things like, actually one of my favorites is this concept of chaos engineering and understanding how do you how do you understand the behaviors and the pathologies of these interacting systems, which don't lend themselves to traditional methods of comprehension? Or, one of my favorites, model-based design. How do we use standards and tooling to compose these systems and build them virtually before we build them physically? How do we use them to pull risk forward? I think there's a huge opportunity for medical devices, but we're still really much, I think, at the infancy of understanding the interoperability. I call it Pandora's box. So when I was working for Honeywell 25 years ago, interoperability started to come in, and it was a pretty dangerous thing. It again shifted the competencies, the value stream, the relevance of the different players. It had a pretty big effect, and now we're starting to see that both good and bad in medical devices in general and automated insulin delivery in particular.
Awesome. Thank you for answering that. That's very interesting. I remember this year I was in systems engineering conference in COSI, held in Minneapolis, and we had a lot of discussions around interoperability. And it never occurred to me at that time that we're talking like what's coming up in future, but it looks like we already have. This is one of those areas where interoperability has been strongly implemented, right?
Mm-hmm.
Yes. That's pretty good. I think we have a lot of questions in the chat, so let's.
Yeah, let me tackle them. How did the Tandem device deal with alarm fatigue? Well, the primary way it did it was using feedback control to keep blood glucose in a tight range. So he no longer was having these wild excursions, going from the top of the range to the bottom of the range and setting off these mandatory alarms. So that was the one way it did it. The other way it did it, we sort of hacked the device. In many respects, you can, or many of the alarms you can configure to be auditory alarm, vibratory alarm, or even suppress it. So we went in before we gave them the system and turned off every alarm we could. Every alarm that we could turn off, we turned off. And then the ones that we couldn't turn off are seen less often because the system is doing a good job of transferring that variability from a place where it hurts to a place where it doesn't hurt as much. I see another question here. Any interesting classes or resources that we can take to learn to code, to design solutions at the intersection between algorithms and physical systems? I know of some grad level work that's happening. So for instance, that reference that I made to the Toyota paper, where is it? They're doing some, where is it? Right here. They're doing some great work on how do you design and compose and verify and validate these cyber physical systems. But I think that's maybe the key word is go looking for cyber physical systems. Okay, Akhilesh, I'll let you take over the facilitation of the questions.
Yeah, I think, yeah, that any classes, resources, and maybe I'll add to Lane what you said, right? So, I'll have to just reframing the answer in my mind, but I think there are some courses like the suggestion was made for a workshop. So if you'd like to do a hands-on workshop, I think with MATLAB, we do have some controls. I mean, controls technology in general, like Simulink is the tool of the choice. And since MathWorks has been working a lot with the automotive and aerospace companies as well, we already have pre-baked workshops, tutorials, online courses. So I will be happy to share some of that your way if you want.
The only caveat I would put to that is these systems that we're dealing with are pretty complex, and it's really when you get into the complexity of things and the doing things at scale that these tools become really relevant and important. So I use a metaphor of building a doghouse requires a different set of tools, methods, and practices than building a house, than building a skyscraper. And the big challenges and the things that I've been fighting and working on for the past 30 years are skyscrapers, not doghouses. And this is where I think there are some extremely powerful tools available for doing that. So, to build on what Akhilesh was saying, go look at how these commercial aviation and automotive companies are dealing with this complexity today.
Absolutely. Awesome. Any more questions from anybody?
Yeah, so this is Bill Whitford with the group here, and Lane, fantastic presentation, and I suspect you could give a 45-minute presentation on each slide, so thank you. What I'd like to mention is I'm working currently on criticisms of AI. You know, people look at ChatGPT and they had a 6-month pause and they're predicting Skylab or Sky something will take over the world.
Skynet.
And what I'm trying to distinguish are criticisms of AI systems that are criticisms of AI, or actually involve criticisms of the rest of the control or prediction or advice system itself. And often there's a real conflation there. And so I liked your example of the workaround and cheat on an automated insulin or diabetes management system. But I noticed that this workaround and cheat criticism of the system, well, you can do that manually. You can lie to yourself about how much carbs you're eating and lie to yourself about how often you have to examine levels. So it's really not a criticism of an automated system. It's simply that you can, I mean, and I know you know this, but I'm reciting that that you can manipulate an automated system to imitate the lies and the cheating that you do manually. And so it's a bit of a criticism of the system, but it's simply saying the system hasn't cured that problem. So you maybe make a comment on that, but my real question is it possible that a person of your order and rigor and capability and honesty in approaches to systems could possibly run for prime minister or president?
So actually, I had a whole chunk of presentation material that made it onto the cutting room floor, talking about exactly this issue, William, about you know, the ethical issues, the political issues, and I deliberately stayed away from that. And also, you know, you make a great point that algorithms aren't that different from humans cheating and doing the fake carb thing. One issue, though, is that humans tend to overtrust automation. So they outsource to these things blindly. So there's this bias called automation overtrust, where you go from these shifting errors from acts of commission, where the human did something that caused a bad thing, to acts of omission, where they didn't intervene and they let the Tesla drive into the wall because they were watching a movie, or they let the control system in the refinery keep going. Or an example in automated insulin delivery, there's different ways that the pathway can stop working, where the insulin stops being absorbed. Well, automation algorithms don't know that. They'll just keep ramming more insulin in, even if it's not doing the job. So this is where people can get in a lot of trouble if they don't intervene. Whereas you wouldn't have had that happen if you were doing manual interventions. You would have known that. But you bring up excellent points.
Thank you, Lane, for answering that. Any more questions? And these are great questions. I think this session, Lane, I enjoyed myself a lot. So definitely there's a lot of value for all of us.
My pleasure. And again, I'm not against AI ML algorithms. I wanted to keep this sort of at algorithms in general and just the challenges that any algorithm would face. And to William's point, it maybe isn't even algorithms. It's what humans are doing. And just being careful that, what do they say? Technology is not neutral.
I had one general question about the way AI does control. I feel like it's based off of some sort of function, right? So like a loss function or reward
loss function. Excellent question.
Yeah.
Yes.
So, and I feel like other control systems have more sophisticated feedbacks, even though the algorithm that's going in is more maybe simpler. It seems like that could be one area of focus to improve AI.
Absolutely. Well, I think this ties into this point about good experiments yield good designs, yield good models. once you've got that model, what are you going to do with it? What objective function are you giving the controller? So for instance, in diabetes, it's a very asymmetric loss function. And what that means is that being high, having high blood glucose will kill you slowly. Being low will kill you quickly. So there's this strong asymmetry. And if you didn't know that, or if you didn't use that in your controller design, you will end up getting the wrong outcomes. So I'm so glad you mentioned this concept of loss functions or objectives. We're starting to see this now with automated insulin delivery. Back to the question about how do we deal with this alarms? Now that we're seeing fairly consistent glycemic outcomes from these AID systems, now the question is, well, at what cost? What was the burden to get there? How many alarms? How many interventions? How accurate did the carb counting need to be? So now we're starting to see sort of these combined loss functions, like a Pareto frontier, where we're, hopefully in the future being able to balance to say, well, I'm super engaged in diabetes and I want the best control for my child. So I'll take on all this burden of human factors and alarms. Or others who say, like, I just want to get on with life and I don't care if it's not the best control. I'm prepared to relax a little. You see what I mean? So I'm so glad you brought up the point about loss functions.
Hey, Lane, I've got a question that outside of your current talk, but I know you'll have a thought on. And that is, I've worked on critical process parameters in bioprocess control. And there's always been a question about a critical parameter, a very important parameter that has always been well controlled. How do you handle that in alarms and in control? Because it can't happen, but it very rarely does, or never does. What do you call it and how do you deal with it?
Yeah, so I've got another whole talk on this exact problem, which we got into at Honeywell with these control systems, where I don't think I'm exaggerating to say there's a million configurable things on an oil refinery control system. You can go in and manipulate a million things. And so the question then became, well, which of those are critical? Like, how do we put those under governance and change management? And the problem is you can't really. And so my solution to that is minimize the number of parameters or use best practices from software engineering, like loose coupling and tight cohesion, avoid building big balls of mud. Again, be careful with the inventory of technical debt that you're keeping around in your software. The number of permutations, again, I've got a whole other presentation on this. I don't know how to do it. I don't know how you identify critical parameters, like that toy example I showed with the little plus sign. How would you know? You just go. So there's methods for dealing with this, like model-based design, automatic code generation, which skip that entire potential source of error. But I don't have a good answer, unfortunately.
Sounds good, Lane. I think we are already past our time, but this is great discussion. So maybe Lane, if you can go back to your slide where you had your email.
Yeah.
As well. So, and I think Justin has a brilliant suggestion for next session being critical process parameter lecture. So we definitely, if Lane, you're up for it.
Yeah. Well, actually, I just thought of something. UQSA is how you could be doing this: uncertainty quantification, sensitivity analysis. So basically, figuring out your partial derivatives. And back to that paper on explaining versus predicting, it gives some specific examples of identifying critical parameters. But I agree, we can make that a future lecture.
And speaking of future, so our next lab is actually on 25th August. We have a reminder, we only have 3 lab sessions left for this year. So if you have more other topics similar to this, which you will be interested in either presenting, or if you know somebody who would be interested in presenting, I guess feel free to reach out to myself or Timothy for that. But thank you again, Lane. This was a really wonderful session. I think I learned a lot, and everybody, this is great discussion going on. Having said that, in the chat, we'll drop a link just now. If you would like to invite your colleague to join this session, these sessions, labs, the last 3 sessions especially, you can actually do so by the link which we'll put in the chat just in a bit. But then just another reminder, like, so this session was recorded and hopefully by end of today, it will be posted online. So if you'd like to revisit this session, please feel free to take a look on our website. So awesome. And there's the link on the chat. So thank you, everybody. Thank you again, Lane. This is great. And I look forward to meeting everybody in our next session on 25th August.
Thanks, everyone.
Thanks, Lane.
Bye.
Awesome. Thank you.
Thanks, everyone.